Hello, everyone. Welcome to our deep dive into adaptive part learning for fine-grained generalized category discovery. Let's start with a simple visual test. Look at these two birds on the screen. To an untrained eye, they look almost identical. Dark feathers, similar size. But if you look closer, specifically at the head, you'll see the bird on the left has a prominent crest and an orange beak, while the one on the right lacks that crest. This is the core of fine-grained recognition. The devil is in the details. Today, we're going to explore how we can teach a machine to see these subtle differences without human supervision using a plug-and-play enhancement called adaptive part learning, or APL. First, let's define our problem setting, generalized category discovery, or GCD. In traditional machine learning, we'd often train on a closed set of labeled data, like dog, car, and tree. But the real world is an open world. When we deploy a model, it will encounter images it has never seen before, like motorcycles or new species of birds. The goal of GCD is twofold: classify the known, accurately recognize the categories we have labeled, discover the novel, automatically cluster the unlabeled data into meaningful new categories. This is the hard part, finding structure in the unknown. Now, GCD becomes exponentially harder when we apply it to fine-grained scenarios. We are dealing with two specific statistical challenges here. Low interclass variance means different categories look very similar. For example, distinct bird species might differ only by the color of a beak or the shape of an eye. High intraclass variance, conversely, the same category can look very different. A Corgi and a Great Dane are both dogs, but they look nothing alike. This creates a confusing signal for the model. Should I group these together because they are both birds, or separate them because of the beak? This confusion leads to a fundamental technical trade-off. On one side, we have generalization. This is the ability to transfer knowledge. For instance, knowing that legs and wings are common bird features helps the model accept new bird species. However, if the model generalizes too much, it misses the novel distinctions. On the other side is discriminability. This is the ability to tell things apart. It's great for separating novel classes, but if the model becomes too obsessed with specific differences, it fails to see the shared characteristics needed for transfer learning. Existing methods usually sacrifice one for the other. Our goal is to break this compromise. So, why do current methods fail? We identified the main culprit, the reliance on the global CLS token. In Vision Transformers, or VIT, this single vector attempts to summarize the entire image. While it captures the global context, the gist of the image, it often suppresses local details. Think of it like describing a person by their silhouette. You might know it's a human, but you can't tell who it is, because you've lost the specific facial features. In fine-grained tasks, those missing details are exactly what we need. Our insight is straightforward but powerful. To see the difference, focus on the parts. Instead of relying on one global feature vector, we introduce adaptive part learning, APL. We propose learning a set of distinct features, each representing a specific semantic part of the object, like the beak, the eye, the wing, or the feet. By decomposing the image into these parts, we can simultaneously achieve two things: identifying discriminative parts, like the head, to separate classes, and identifying shared parts, like the body, to generalize knowledge.
Let's look at the technical execution. Step 1 is unsupervised part discovery. A key constraint here is that we do not use any part annotations or bounding boxes. Instead, we leverage the pre-trained DINO model. DINO's self-attention mechanism has an emergent property where it naturally localizes semantically meaningful objects. We use this as a prior. We introduce a set of learnable queries that interact with these DINO priors to consistently locate corresponding parts across different images. So, query 1 might learn to always find the wheel, and query 2 always finds the headlight, regardless of the image.
Step 2 is where the learning happens. We employ two novel loss functions to shape our feature space. First, the all-min contrastive learning objective. Standard contrastive learning pushes different images apart globally. Our method is smarter. For negative pairs, images of different classes, we only push apart the most similar corresponding part. Why? Because if two different cars share similar wheels, that's fine. We shouldn't penalize that. We only want to force the model to find the one part, like the headlight, that truly distinguishes them. Second, the diversity objective. This prevents the model from being lazy and mapping all queries to the same easy feature like the background. It forces the queries to be orthogonal, ensuring we capture a rich, diverse set of parts. From an engineering perspective, we designed APL to be a plug-and-play enhancement. This is not a rigid new architecture. It is a modular block that replaces the final feature extraction layer of existing GCD frameworks like SimGCD or SPTNet. You simply remove the CLS token feature and plug in our concatenated APL part features. This allows us to instantly boost the performance of various state-of-the-art baselines with minimal code changes. Now let's talk numbers. We tested this on the most challenging fine-grained benchmarks. The results are significant. Looking at the CUB 200 dataset, the BIRD dataset, we see a 4.4% accuracy boost compared to the strong SimGCD baseline. On FGVC aircraft, we see a massive 5.4% improvement. It is crucial to note that these gains are largely driven by the improved recognition of novel classes. This proves that our part-based approach isn't just memorizing training data, it's genuinely better at discovering new categories in the wild. To visualize why the accuracy improved, we used TSNE to plot the feature space. The top image shows the baseline representation. You can see the clusters are messy and overlapping. This is where the model gets confused. The bottom image shows our APL representation. The difference is night and day. The clusters are tight, compact, and well separated. By explicitly modeling parts, we have cleaned up the feature space, making it much easier for the clustering algorithm to do its job. Finally, we conducted an ablation study to ensure every component contributes value. Starting with the baseline at 55.1%. Adding our all-min contrastive loss boosts discriminability significantly, reaching 57.8%. This confirms that how we compare parts matters just as much as finding them. Adding the diversity loss ensures we don't miss information, bringing us to the final 60.1%. This confirms that the combination of learnable queries and our specific loss functions is the optimal recipe. In conclusion, adaptive part learning solves the critical trade-off in fine-grained discovery. We shifted the paradigm from global ambiguity to part-based clarity. We provided a versatile plug-and-play module that enhances existing models. And most importantly, we set a new state-of-the-art for discovering fine-grained categories. Thank you for your attention. We hope this gives you a clear understanding of how focusing on the details can make a big difference